Hello everyone, my name is Abhigyan Jha and today, along with my batchmates Rishikesh Bhate and Anurag Bagal, I am here to present our SNS mini project Audio Equalizer. It has been performed under the guidance of Professor Najib Ghatte. So, what is an audio equalizer? An audio equalizer is an electronic device or software that adjusts the balance between frequency components of an audio signal. It lets user boost or reduce specific frequency ranges like bass, mid-range, and treble to alter the tonal quality of sound. Equalizers are used to improve audio clarity, customize sound quality, and reduce undesired noises. Now let's have a look at uses of an audio equalizer. It is useful in enhancing the sound quality. Equalizers fine-tune audio to improve clarity and detail, especially helpful in sound systems where acoustics or speakers may not be perfect. Then, it is also useful in tailoring audio to taste. By adjusting frequencies, listeners can customize sound to match personal preference, such as emphasizing bass in music or making voices clearer in podcasts. Then, it's also useful in removing unwanted noises. Equalizers can reduce specific frequencies that carry background music which are unwanted, and it helps in making the primary audio clearer. And lastly, it also balances sound across environments. It helps adjust audio for different environments, like making audio crisper in outdoor spaces or removing reverb in larger rooms. Now let's see applications of an audio equalizer. First, music production. EQ is essential for balancing instruments, voices, and sounds in a mix to ensure each element is clearer and harmonized and there is no clash in between. Then, live sound engineering, adjusting frequencies during live performances to manage venue, acoustics, and avoid feedback. Thirdly, broadcasting and streaming, enhancing vocal clarity and removing background noise.
So let's explore how FFT or fast Fourier transform works as an audio equalizer. In essence, FFT lets us break down an audio signal to understand and control its frequency content, which is crucial for effective audio equalization. We start with an audio file which exists in the time domain. This means it's simply a record of how loud the sound at each moment. However, to adjust specific sound qualities like bass, mid-range, or treble, we need to understand the audio in terms of frequency. FFT helps us make this transformation. Here's how it works. The first step is FFT transformation. If using FFT, we convert the audio from the time domain to the frequency domain. This gives us a new representation. Instead of showing amplitude over time, we now have amplitude values for each frequency. Think of it as a frequency map of the audio, where we can see the bass, mid-range, and the treble components distinctly. The second part is isolating frequency bands. Once in the frequency domain, we can isolate specific frequency ranges known as bands. The first one is bass, which is typically around 20 to 250 Hz, covering deep and low sound. The second one is mid-range, which ranges over 250 to 2000 Hz, where most vocals and instruments are found. The third one is treble, which is 2000 Hz and above, capturing high and crisp tones. The next step is applying gain. For each of these bands, we set gains, essentially a volume adjustment specific to that range. For instance, boosting bass means amplifying the amplitude within the bass frequencies, while reducing the treble means lowering those frequency amplitude. The next step is applying inverse FFT. So once we have adjusted the amplitude of each band, we use the inverse FFT to transform the signal back into the time domain so we can hear the changes in the audio. The next step is normalization. Finally, we normalize the output so the volume remains balanced and avoid distortion. This FFT process allows us to tailor the audio tonal qualities, enhancing or reducing specific frequency ranges. So let's understand how the circuit actually works. The first one is use of MAC 9814, which is a microphone amplifier. So it captures external audio input with automatic gain control to prevent distortion. The next step is the signal is traveled to NCP 3008, which is a 10-bit ADC, which means analog to digital convert. It converts the analog signal from the MAX 9814 or other input sources into digital format. The next component uses microcontroller, which is Arduino, which process the digital data, applies equalization algorithm, and controls the overall audio processing flow. The next component is MCP 4725, which is a 12-bit Digital to analog converter. It processes digital signal from the microcontroller back to analog format. Afterwards, PAM8403 is used, which is an audio amplifier which is used to amplify the sound. The last one is 4 ohm 2-watt speaker, which is used for the final process and amplified audio signal. This sequence reflects the logical flow of audio input, processing, conversion, amplification, and output in the system. Now, my friend Anurag will explain how the code works.
Now let's start with the crux of this mini project, which is creating an audio equalizer that adjusts bass, mid-range and treble frequencies independently. So we've written this code in Python using libraries like Soundfile for audio handling, NumPy for data processing and applying FFT, and Matplotlib for visualization. So here's how it works. First, we load in the audio file to get its waveform data and sample rate, setting up the audio for processing. Then to next we use FFT to convert the audio from the time domain to frequency domain, where each frequency component is accessible for adjustment. Next, we split the audio spectrum into bass, mid-range and treble bands. Each band has a gain setting right now set to 1 for no change, but adjustable to boost or cut frequencies in each range. And here in this for loop, using a mask, we selectively apply these gains to the corresponding frequencies, controlling the amplitude in each band independently. And finally, we convert the modified frequency data back to the time domain using the inverse FFT from the NumPy library, normalizing it to maintain a balanced output volume. And finally, we save the equalized audio and plot both the original and the process waveforms to visually show the effect of our equalization. This is the input audio. This is the output for bass frequency cut at 0.25. And this output is for mid-range frequency cut at 0.25. And finally, this is the output for treble frequency at 0.25. As you can see, the difference in the audio is both audible and visually noticeable in the waveforms. The equalization clearly impacts the frequency distribution, with adjustments to the bass, mid-range and treble, creating a distinct change in the overall sound. This demonstrates the effectiveness of using FFT for audio manipulation. And with that, we conclude our mini project. Thank you for watching, and I hope you found this exploration of audio equalization insightful.